Hello, hello, hello.
Hello.
Milks and
MoNaCos.
Unit 9, talking
Page
about video
7.
number 3.
Páginas.
And here we start. Now we get into the unit.
Right. So you've done your due diligence. You've taken your vocab quiz by now, I hope.
If not soon, if you're not ready, soon.
Study. Do it.
We're going to learn about what kinetics is, and let's get into the definitions specifically of collision theory.
Yeah.
Let's do it.
So what are chemical kinetics and rates of reaction? Well, Mr. Milks?
Basically, how fast the chemical reaction goes. And then what can we do to either speed it up or slow it down?
It's always going to be the next question.
Yeah, I mean, some of these product or reactions make products that are worth some money.
And so we, the chemists, want to make some money. We need to speed that reaction up so we can make money faster. Or we need to slow the reaction down because what it makes is so valuable, but it's so violent.
Yeah, sure.
Right? You were telling me stuff that you used to do at Kodak. You'd have to sit there and watch peroxide drip at 1 milliliter an hour for like a week.
20, they would take 28, 36-hour editions, and they had to be
because you had to slow it down to the point where it wouldn't blow up the dang building.
Right.
And the product you were making is so valuable, you had to do it slow, so you made your product.
Yeah, or otherwise it was going to end up all over the roof and the road.
Right. Right. And you'd end up in the
We
hospital.
were talking basically if it was rocket fuel.
Right.
We were at, so
you got to be able to speed up or slow down a reaction depending on what you need it to do.
Right. So, or how danger is another good one. So, what determines the rate of a chemical reaction? Two things really: the nature of the reactants and the reaction mechanism itself.
And when we say nature of reactants, no matter where we're at in this year's study, we're talking about, is it ionic or is it covalent?
That's really what it is.
That is what the nature of reaction is. So, ionics things, because they're already charged, they're freely mobile, and they're very tiny generally.
And they dissociate.
They dissociate. They react very quickly for this reason.
Yeah, we're going to see that their steps and the mechanisms, if we were talking about a mechanism, their steps are less.
Yeah, fewer.
It's a one-step thing versus a covalent.
So, if ionics react fast,
covalents react
slow. There we go.
There you go.
Number of steps in a reaction, so the mechanism. So this is kind of, I hope, a no-brainer, but if you have more intermediate steps,
it's going to take a long time.
Think about baking a cake.
Sure.
Are you baking it from scratch, like you've got flour and leavening and all this stuff, or did you buy a box of cake mix and you throw some eggs and oil in it and you got cake in the oven within 5 minutes?
Right. Or do you got to ground the flour yourself?
Wow, crazy like
make
that,
some,
right?
churn some butter, and go milk the cow. And I mean, we could really slow this thing down.
If you've ever been to a restaurant or worked on a cook's line, you know that making certain food takes more steps, so it takes longer to cook.
Sure.
Right? I'm making a big salad with 10 different ingredients in it. Well, you got 10 different things to chop up and mix together in the right portions to get that salad out to the customer. Versus, we're just having some mozzarella sticks.
Yeah, throw them in the fryer.
Throw them in the fryer, pop them on a plate, give them a little side of marinara, and we're good.
Yep.
Faster.
So basically, the less steps, the faster it'll be.
Yep.
That's really what it means. And we're not going to get into the actual steps. You just need to know at a theoretical level that this thing does actually happen.
Why is this reaction fast? Well, it's probably because they're ionic things that are involved in it, and there's very few steps in the reaction.
That's what I want you to be able to say.
Why is this reaction slow? Well, it looks like there's covalent reactants, and so there's probably more steps in the mechanism. There you go. Period.
All right, collision theory. What it says, MoNaCo?
It says atoms or molecules got to hit each other for a reaction to occur. Because, I mean, think about it. The reactants need to come together. That's why there's a plus sign in all our equations. This plus that implies they have to hit each other.
Yeah, they literally have to make physical contact.
For
they just come near each other. Not happening.
Doesn't count.
Doesn't count. It's a near miss.
It's not a collision. It's not a reaction.
So then now we're going to go a little bit step farther. And a collision that is effective, right?
Because we might hit each other.
And that doesn't even count sometimes.
Right.
Because not all collisions are created equal.
Right.
I mean, some just don't create the reaction. And so for a collision to be what we call effective or cause the reaction, it must have two very specific things. It must have enough energy for the atoms and molecules to react.
Right.
They got to have enough speed or heat. Okay. And then they have to have the proper orientation. The atoms or molecules have to be facing in the right direction, hitting the sweet spot, if you will.
Yep. And going off of that, it's baseball, softball season. The great analogy for an effective collision is hitting home runs.
That's what the pogo's all about.
That's what the pogo's about. You're not going to hit a home run every time you hit the ball.
No.
Why? Sometimes a pitcher doesn't throw the ball hard enough for you to get enough energy to bounce off the bat.
Sometimes he's got a weird spin on the ball, so
And
you
it
hit the
doesn't-
wrong side of the ball,
and
it
it
goes
doesn't-
flying in the wrong direction.
Exactly. So hitting a home run is an effective collision because you hit it with the right amount of energy to send it over the center field wall.
Right
and
in
it's
the
a
sweet
sweet spot, so it's just flying. So in order for a reaction to occur or even start, got to hit both criteria, effective energy and orientation.
Both are key, and these are the testable things.
Enough energy with the without the right orientation, they just bounce off each other. Right orientation, but not enough energy, they just bounce off each other.
Right, they need both. Need both. All right, so now we're going to play a game with each of these, with our 6 things that we didn't relist. This was in the first video. So there are 6 things that we can do to manipulate the rate of a reaction. They're listed across the top here.
And you're going to play with 4 of them in the lab.
Yay! But these are the 6 things, right? We went over them in the previous video. You want to go over them again or no?
Well, let's see. Nature of reactants. If I increase the rates of a if I want to increase the rate, I should somehow try and figure out how to switch my reactants to ionic things.
Right, because ionics react faster.
Faster.
If I want to slow it down, well, then maybe I should use covalence.
Right. Can I get what I want with covalent things? You're never really going to be asked to do that.
You just need to
You
know.
just need to know ionics go fast, covalents will go slow.
There you go. Now concentration.
You will be asked this.
Yes. So these all, and you might want to take some little side notes. These relate back to collision theory.
Right.
So if I have a higher concentration, that means I have more stuff in the volume, in the same volume. If I have more stuff, the probability of collisions are with the right temperature or right speed and right orientation increases.
Right.
So my reaction rate goes up.
It's like a ball pit. More balls in the ball pit, more fun the kids have.
There you go. And so decreased concentration, the less chance I have for collisions.
Right. You don't
Make
have
common
anything
sense,
to bump
right?
into.
Okay, so temperature. Temperature is kinetic energy, right? So the more kinetic energy I have, the more likely I have the proper energy I need for that collision. Okay, also kinetic energy, they're moving around. The molecules are moving around faster, so the number of collisions should go up. So increasing temperature will increase my rate of reaction, and just the opposite.
Yeah, like the energy, the amount of energy.
They slow it down, and they start going slower.
There's not enough energy in that
for
collision
the reaction
for
to
the usually
happen.
home run.
Right.
Pressures for gases only, because pressure for gases is like concentration.
I can
You
squeeze
increase the
them.
pressure, you squeeze them together, they literally get closer together, so they're more likely to bump into each other and cause an effective collision.
Nice.
Decrease the pressure, decrease the rate.
Right, because now they're farther apart. What's the chance they're going to hit each other?
Very slim. to
Very
none.
slim.
That's ideal gas law would say low pressure, high temperature is ideal gas scenario.
Right.
Not really going to get much chemical reactions going on in there.
Right. Surface area. This is
Particle
like
sizes.
crushing up a tablet.
Right. Everybody knows if you got Alka-Seltzer and you need it to dissolve quickly, you grind it up, crush it up, break your tablets in half, and it plop, plop, fizz, fizz goes away. It dissolves faster, and you drink it down, and you get rid of your headache and
Right.
your tummy ache. So you increase the surface area by grinding the particles down.
Right. If I do that, what I effectively do is make more collision sites.
Right.
More chance for collision. Opposite's true. Decrease the surface area, I can decrease the rate of my reaction.
Right. Beautiful. Last thing, a catalyst. You're going to see this in lab. Some things, you add a catalyst to them, the reaction rate speeds up.
Yeah.
Other things, you take the catalyst away, or you don't add a catalyst,
Yeah.
the reaction slows down.
Yeah, we're not really going to see this in lab because the catalyst is already in there.
Well, I have a second example in the lab where you can see the effect
Oh,
of
without
adding
the-
a catalyst.
oh,
Yeah, it's
cool.
a different reaction,
Okay,
but
cool.
we'll see the decomposition of hydrogen peroxide.
Okay, good.
You get a little beaker of it, and you add a pinch of the catalyst, all of a sudden it starts bubbling and fizzing and decomposing.
Right, otherwise
And you
it
can
goes-
see that the catalyst doesn't change itself over time either.
It's still there when it's done.
It's still there at the end.
Good.
So,
That's the definition.
yeah.
While we're here, this is the one thing I wanted to do. Catalyst likes to be in history likes to be students' number one go-to answer. I want to stop that
Okay.
because not everything has a catalyst. Not every reaction
No.
it has a catalyst, and not everything is a catalyst for every reaction.
Right.
Those things are very specific. So I want you to think temperature. I want you to think concentration.
Those are the go-to.
Yeah, surface area third. Okay,
Yeah.
those are the big ones. So those are what I want you to remember. So now I need to know what kinetics is, be able to describe it in terms of collision theory. How am I making more collisions? How am I decreasing the collisions? We didn't show you a lot of that. We talked about it. So if you don't get it, you gotta come and make MoNaCo, or I draw it on the board for you, or come up with another way to simulate it for you. So you
Better
can get
yet, go ahead and search it out. Find
Sure.
animations on the internet.
Go
Collision
nuts.
theory. There's so much out there. It's 21st century. What's your excuse for not knowing these things?
Seriously, there are 6 factors. You need to know all 6 of them because all of them are testable. See you guys.